Okay, so this one probably won't last for too long, although sometimes I get surprised. Now this is going to be a supplemental one for our inductors. In this case, we're going to look at, in one of the other videos, we looked at kind of what an inductor does, how it affects a circuit, and what happens at time equals 0, and then comparing that to what happens as time goes to infinity. In other words, a lot of time passes. Now, inductors, and I keep using this phrase, but it's how I remember what they do, they don't like to let the current values in the circuit change. Now, they're not 100% effective at that, but you can imagine that it's kind of like a throttle control where it's not going to let you change very quickly. You can slowly speed up, or you could slowly slow down, but it's not going to let you go from 0 to 60 instantly, or from 60 to 0 instantly. It's going to make you kind of gradually approach whatever values you've got. And of course, I'm talking about speeds, but in reality, this affects the current in a circuit. I'm going to draw, hopefully, a pretty simple circuit for us to look at with an inductor. I'm going to have a resistor in here and an inductor. Now, this time I'm not going to put in any numbers. We've got R and we've got L. R is the resistance of this circuit, or this resistor, I should say, and L is the inductance of this inductor. And I'm going to say that we have a total potential difference of squiggly E, or we could call it delta V battery, but this is a little bit easier, so we'll go with that. All right, here's what I'd like to know. I want to know what happens to the current as a function of time. Now, off the top of our head, let me throw a switch in here. Off the top of our head, we start off with no current, I close the switch, and it's going to slowly grind up to a start as things start moving around. Remember the inductor, if we start with 0 current, it is going to want to try and keep it at 0 current. It's not going to be 100% effective, so things are going to start speeding up. And we're going to eventually achieve a steady state where the inductor basically pretends it's a wire, has no resistance anymore, which it's fine with because the current will finally get to its total value and stop trying to change. So the inductor's like, fine, as long as you're not trying to change, I'm cool with that. And then we would just have the equivalent of, this would have an equivalent resistance of 0, effectively. Technically, it's an impedance, but neither here nor there. And then it would just be a circuit with this one resistor. All right, so I want current as a function of time. We're going to apply calculus on here to actually find that, and this one's usually a little bit more straightforward, luckily, because our equations already start off with the differential values. Real quick, though, let's find our boundary conditions. So my initial current is going to be equal to 0 amp. How do I know that? Well, we closed the switch. We started before we closed the switch. There's no current going through, which means the inductor is going to hold it at that for a fraction of a second until it slowly starts climbing up from 0 and starts building to whatever current we end up with. Great. I of infinity. By infinity, we just mean we give it a really, really long time. At the end of this, we're going to talk about how, just like with capacitors, we have a time constant that we actually get from this, where we can get an idea of how long it's actually going to take to do most of the charging. But in general, we usually just say at the beginning and a really long time later is usually the terminology, and it means until things pretty much approach a steady state. Let's find the current at the very end, and in doing so, or to do so, we'll need to do loop rule. Loop rule again. Minus squiggly E of the inductor is going to be equal to 0. Now, we took a look at this in the other video, but I apply loop rule. I go across the battery, it gives me squiggly E. I go across the resistor, it drops me down by whatever the potential difference is across that. And we have an electromotive force, an effective potential difference across the inductor of some value. And then we end up back where we started, so it all equals 0. I go through and actually set this up. So we've got squiggly E minus the initial current times, oops, not delta V, the resistance, minus, I'm going to go ahead and do, let's see, the potential difference across L. Oh, actually, let me go ahead and replace that with its technical equation, L di dt. Now, one thing that we will find out We may not be able to solve this completely, but if we want to find, we know that this is 0, at least initially. This value is 0, and so we could go through and we could actually find di dt, which is something that we've done before. I apologize, I got a little confused. What I'm looking for is I infinity, the current as time goes to infinity. It'll look very similar, although we're going to have this minus I of time infinity r, which is not 0. The initial is 0, and that makes this a non-zero value. But when we get to this later, the current stops changing because we reach a steady state. The current gets to its maximum, and it just kind of stays there. And the inductor says, oh, well, you're not going to change anymore? Okay, I'm cool with that. And it stops actually having a potential difference across it. di dt, if I is a constant, then the derivative of it will be 0, and we actually end up with 0 volts across our inductor. With this, we can find that I infinity is going to be equal to, add that over to the other side, divide by R. It's going to be the potential across the battery, the potential difference, divided by whatever the resistor value is. That'll be somewhat useful later, and it may also be something that, I'll go ahead and mention, that is something that we'll probably work with here in the actual setup. But it's going to be equal to delta V over R. All right. These are things that I'm going to use later to check my boundary conditions. In other words, I'm going to see if whatever equation I get for current as a function of time, if I put in t equals 0, do I get 0 amp? And if I put in t equals infinity, do I get squiggly e divided by r? All right. Now that we've done that, I'm going to do this a little bit faster because hopefully you've seen this sort of thing done with the capacitor videos. If not, check out the capacitor videos, but we're going to have the same thing, or something very similar, I should say. We do loop pool like you just saw. It'll be equal to, at any given point, the potential across the battery, which is a constant, minus the current at some time t, I'm just going to leave that as the current, times the resistance of resistor R, minus, negative L di dt equals 0. Hang on just a second, let me check my notes. Oh, I apologize, I'm actually going to take a positive here. I'm going to use the absolute value of that. Is that what I've got in my notes? I think so, yeah. In short, I need one negative here, and the reason why is the battery is supplying energy, and these are potential differences. We actually have the resistor removing energy, so I need this to be a negative, and we have the inductor storing energy. It's taking energy away from the circuit, so I'm just going to keep the one negative here. Now, the negative that goes along with this is going to factor into the fact that di dt has a specific shape. In this case, it's actually going to be an increasing one versus decreasing, but in short, bear with me on this, what we're looking at with loop rule, we know that the battery is giving potential difference, giving energy, the resistor is taking it away, and so is the inductor. So I'm going to use these values with the minuses so that I can actually get the resistor is taking energy and the inductor is taking energy. All right, now that I've got that, I can do the following. All right, what I'm going to do, I'm going to replace squiggly e with the following. I can move this around and I can find that squiggly e is also going to be my final current, which I marked as I infinity in the other one. I'm going to leave it as I1, our final current, minus IR. So I infinity times the resistance of the resistor. This is the potential across the battery, which we found with this. I final is equal to squiggly e, the battery, divided by R, and we got that from what happens as time goes to infinity. There's no potential difference across the inductor, so forth and so on. All right. Minus L di dt. When you're asked for a differential equation, okay, well, this is a constant. This is not a constant, but you're usually looking for current as a function of time. The resistance is a constant, the inductance is a constant. In fact, this is what you're looking for if you're asked simply for a differential equation that can be used to solve for current as a function of time. We're actually going to evaluate it here. I'm going to do a little bit of math here, but but I'm going to have I final, our total current, minus whatever the current is at some given time, times R, equals L di dt. All right, I'm going to move some things around. Basically what I want is as many of the constants as I can on one side with dt, and I'm going to have di and any of the I stuff, along with anything stuck with it, over there. So I'm going to move things around. We're going to end up with the following. R dt over L equals di over I final, our total current at the end of time, minus whatever happens to be our current at any point in this whole thing. This is a variable that is changing. This is a constant that happens at the end of time. All right, here's where we're going to do the integral, just like we've done in class. I'm going to integrate this from 0 to some time t. And in doing so, I'm going to integrate this from my initial, which in this case is 0 current. We're looking at the current. At the very beginning, the current is 0, to whatever the current is at some time t, I sub t. Here we go. This one integrates pretty easily. We end up with R dt over, R dt over L. We end up with, I integrated it from t, evaluated from t minus 0. You're going to find that that is RT over L minus 0. I'm just going to leave the minus 0 off. I'm going to do U substitution on this, where U, we'll do this in a different color. U equals our total current minus the current at any given point, whatever point we happen to be looking at. And that means that du is equal to negative di. Working with that, I get the following. I'll have a negative that gets kicked out here. 0 it du over u. I'm going to move the negative over to the other side, just like I did in the other stuff with the capacitor. And I'm going to evaluate this. We end up with natural log of u, evaluated from 0 to the current at some time t. I'm going to replace u with what it is. Natural log of our final current minus our current at whatever time we're looking at. And we're going to evaluate that from 0 to the current at time t. All right. Negative RT over L equals natural log of final current minus IT, the current at some time t. This is where I'm plugging in the limits of integration, minus the natural log of the final current minus 0, my lower limit. This minus 0 basically goes away, and I can use the rules of natural logs to clean this up a little bit. Come on, board. Got work to do. Oops. My final total current minus my current as a function of time divided by my final total current. I can get rid of the natural log by taking e raised to the both sides. We end up with the following. I end up with, once again, an exponential. E raised to the negative RT divided by L equals I final minus I as a function of t divided by I final. You'll see that this matches pretty much with stuff that we've done in class and the capacitor video. In fact, this looks pretty much the same. It's almost the exact same method. I'm going to multiply this over, and we end up with I final times e raised to the negative RT over L equals I final minus IT. I'm going to add this over here and subtract that over there, and we get our final answer. I, as a function of t, is going to be equal to I final times 1 minus e raised to the negative RT over L. All right, now let's see what we can tell from this. I defined this as the final current. You can actually go back in and replace it with squiggly e divided by r. Those are the values that were actually given. However, I keep doing that in these because I want you to be able to look at what we've got at the end. So, if we plug in, let's check our boundary conditions. T equals 0 seconds. I plug in t equals 0. We said before that my current should come up to 0 amp. if I put 0 in here, we have e raised to the negative 0, so e raised to the 0. Anything raised to the 0 is 1. 1 minus 1, this whole thing goes to 0, which means this whole side is 0, and our current at time equals 0 is in fact 0 amp. Great, we've met a boundary condition. Now, at time goes to infinity, a really long time later, we said that I final equals I infinity. I changed that so I didn't have to draw the infinity symbol a whole lot. Sorry. Should be equal to, well, I final, which is the terms we've got there, but we can also replace it with squiggly e over r. That being said, here we go. Let's find out. So if I put in t equals infinity or t goes to infinity, we have e raised to the negative big number. In fact, it gets so big that it approaches infinity, which means we have 1 over e raised to the infinity, which means this whole thing, as t goes to infinity, the limit of this term goes to 0. We have 1 minus 0, which is 1. 1 times our final current is what we'll end up with, which means that as time goes to infinity, we do indeed end up with the total current, which is actually squiggly e divided by r. It matches our boundary conditions. We also know that this is an exponential decay, so if I were to graph this, my current, or I'm sorry, it's not a decay, but let's see what it actually does. The current as a function of time. We have an asymptote up here that is equal to I final, or in the terms that we were actually given, this value would be squiggly e divided by r. We start at time equals 0 with a current of 0, and we end up with it going like this, and asymptotically approaching squiggly e divided by r. As t goes to infinity, it will finally get to that. It's going to, just like we saw with the capacitor, we end up with a time constant. It's going to get very, very close in a finite amount of time. It may get up to 99.999% of its actual value in a finite amount of time, and that's what we're actually dealing with. In real life, by the time you have that many significant figures, it's fully charged as far as you're concerned, because that tiny little bit left isn't going to make much of a difference. The final thing that I'll bring up, probably need this equation first. So here we go. This also matches what we described before. We have that it starts at a current of 0, and it is climbing up to asymptotically approach what it's actually got there. All right. What I do want to bring up is this. Just like before, last time we had t divided by RC. What you're going to find this time is we have another time constant. Time constant for an LR circuit, which is shorthand for resistor and inductor. Again, L's are usually used for inductors, at least in circuits. The time constant, tau, is going to be equal to, well, just like we saw before, it'll be t divided by tau, our time constant. It's going to work just the same way as we did before, t divided by RC, where RC was tau. Now it's L divided by R. You can find the time constant for an inductor-based circuit by taking the inductance divided by the resistance that you have. And your units on this will actually come up in seconds, just like they did with the capacitor and the resistor. Although with the capacitor and the resistor, it was R times C. For the inductor, because it acts differently, we actually have L divided by R will give us our time constant. But you'll find that the time constant works pretty much exactly the same as it does for an RC circuit, because the equation we end up with is very similar as well. We have this exponential that gets very, very close to our asymptote as time goes to infinity. Here's the calculus of an inductor-based circuit. Now, one quick thing that I will point out, if you set this up instead where you have a fully charged inductor and you have it supply charge to a current, in the other video that I did on inductors, I mentioned that we could flip some switches and it would try and keep things going. You can do exactly what we did with the capacitor. You'll have another negative that shows up, just like we did with the capacitance, because now the relationships are changing. Instead of having our So if we have our current versus time, instead of having it as an increasing function that asymptotically approaches the total, we would end up with, at time equals 0, we start at our total current, whatever that may be, and we will drop down like this and have an exponential decay. You can go through and you can actually solve that as a recommendation. It'd be worth looking at, but you'll find that it does, like I said, pretty much the exact opposite of capacitors, where we're going to end up with this effect instead. We start off with a very high current that it's trying to maintain, and then it will actually drop off the current as time goes forward. All right. I think that's pretty much everything. Although that may not actually be the exact opposite of capacitors now that I'm thinking about it. It's been a long day. However, this is what it would do. It's going to supply energy to the circuit. It starts at a large current because it's trying to keep the current going. So imagine we remove the battery and we put a line here where we got the inductor completely charged up. We remove the battery so it's no longer supplying anything, and the inductor tries to keep the current going. It will release its energy, and as it starts running low on energy, the current is dropping and dropping and dropping, and you'll find that it decays like this. All right.